So this teardown I've been really looking forward to. This I'm tearing down today is the Ignite Lite module. This is a 6Q version of their Ignite system. Obviously this was designed by Cobra Firing Systems, but this is sort of traded more as their consumer market grade system, although I have to confess when I got into Cobra that was always traded at the various. I did it as a consumer market, but these days it's gone much more professional. So here we can see it next to the DB04R, which I've done an awful lot about on my channel, and you can see actually it's got a really nice form factor. It's just sort of based around a 9-volt battery, just a bit bigger than a 9-volt battery, so it's got a really small form factor. It looks really sleek actually. I really like the look of it. The same about the numbers on it are in the front casing, so you can't really see them because they're sort of black. So especially at night, it'd be very difficult. But yes, and you've got LED in the middle, which tells you the sort of the status of the module. And then you have the quick clips, which of course you've got 6 Qs on this one, unlike the 4 on the DB04R. They've managed to get that to smaller form factor, obviously, because they've got rid of the bare end terminals. Now, my only slight criticism from the look of this is if you look at the battery compartment, you can see the board in the module. So they've gone for a black plastic, but then the solder mask is red on the board. It's just like, why would you do that? And I appreciate that Cobra have this thing that they like their red solder mask, but it just sort of undermines a little bit of the professional sleek look by putting red on the solder mask when black would have made that look pretty much invisible to the naked eye. So let's have a quick look at the PCB. Now in the past I've just gone straight into the schematic, but then on the video I did with the DB04R remote, I first did a sort of a look at how I would do a reverse engineer of this, and I sort of guessed a bit, and then we actually did the reverse engineer, and some of the bits I was wrong, and people found that quite interesting to see from a designer's point of view what you can easily get wrong or right. So I haven't actually looked at the circuitry yet. I'm just going to go through the PCB as I would start to do the reverse engineer. So I would first of all find the positive input of the power supply, which of course is the 9-volt battery, and that is over here. So that is the 9-volt input, and that obviously follows this track up here, which as you can see there's the switch there. So this is actually the switch footprint. Then it goes from the switch down there to Q1, and people might think it's a bit weird having what looks like a transistor there. That's actually going to be a PMOS, because this is going to be the reverse polarity protection. They're not going to use a diode in this case, because this is a low voltage sort of battery powered device, and with a diode you've got a forward voltage drop, so you're already dropping your voltage rail down. If you put a reverse protection diode in there, they want that voltage because they want as much current to flow through the Qs as possible. So you don't want to have voltage drop used, like that, used basically messed away by a diode. So PMOS is much better for doing that. So they've got a PMOS there, and then this block here is really familiar to anybody that's seen any of my videos. That is basically a power linear regulator. You can tell that by the smoothing capacitors each side in this general layout. Moving on from that, you have the diode and its drive transistor. So you've got the LED, then you've got the resistor, which will be the current limiter for the LED, then the transistor, which will be effectively, this LED is going to be between the power rails. It's not going to be, no current is going to be sourced from the microcontroller. The microcontroller is merely going to enable and disable this transistor here. So the LED is always pulling current from the power supply rails rather than from the microcontroller. Then moving on, we obviously have the microcontroller here. Some of it, this side as you can see, is actually the Bluetooth antenna which goes out to the actual board. They've put a track there, and this will be impedance matched for the antenna section. This is what you'd call a system on chip, because it's doing a few things, and this has become really popular in the last sort of 10 years or so because of obviously the Internet of Things thing. So you've got obviously the radio section for the Bluetooth, and then a microcontroller, probably an ARM core, there running the rest of the product. I'm a little bit concerned that they've deliberately paid to have it obscured, all the chip detail numbers, because that always shouts a bit amateur to me. And the reason why I say that is because this is such a simple product. Any electronic engineer could reverse engineer this really straightforwardly, even without any details on any of these chipsets. So I don't understand why they think they need to protect it that much, that this is going to be a design that was going to be, really open to people copying if they don't put that obscure mark on there. And for me, when you get to this level of professionalism, I wouldn't expect that in a company like this. That is such an amateur move, because they know full well any professional engineer can to reverse engineer this really easily and really quickly. So you're not stopping a professional from doing this. What you're actually stopping is an amateur or somebody interested in engineering from taking this apart and figuring out the chips if they don't know them. So you're actually affecting the younger generation of engineers by doing stunts like this, because they're the ones that won't know the market. People like myself know the market, so I can probably guess this. There's probably 2 companies that I can think off the top of my head that would be at this price level for this sort of product. That's going to be NXP Semiconductors or Nordic Semiconductors. So there's either going to be NXP or a Nordic, and I could go into a big stockist and I could whittle that down quite quickly by the fact we know it's a 1, 2, 3, 4, 5, 6, 7, 8. That's a 32 pin QFN. So we know we can search for that, and we can obviously search for the Bluetooth part of it, and then we can get some results really quickly. Just look at data sheets basically, and it won't take long. So that worries me that they've done that. Anyway, moving on. So from the chipset, we have some transistors here, which I'm not too sure at the top of my head what that's going to be about. This does monitor the battery level in the app, so maybe that's to do with the monitoring the battery level. Just some resistors. These are going to be sort of in general lines, maybe from the for the drive-in of these various transistors. This device here is going to be another PMOS of some sort. Now the reason why I say that is because if we look at the actual Qs first, so each of these blocks is going to be effectively each Q switch, and these devices look to me like they connect to the ground plane. So this is going to be an NMOS. So this is going to be connecting one side of the igniter to ground, which means we need to connect the other side to power. The fact we've got this big track here that leads up to this device, and this device is up there rather than down here, because this is all ground plane. So this must be using the 9-volt side, which is coming in up here. So this is going to be a PMOS. There's going to be the 9-volt supply for the igniters, obviously. So this is going to create the direct current through the PMOS and then through the NMOSs to ground. So these are going to be switches for this. As I've already explained, each channel is going to be a separate NMOS to ground. So that's how they're going to select which channel they're going to fire, but all of them are tapped from the same PMOS, and that makes complete sense to me. So that's a really good sort of basic look at how they've done this. There's nothing really complicated here. For me, most of this is probably going to be just out of a data sheet. There's nothing that's really over-engineering here, which is really good for a control system, because the last thing you want to do is to complicate your life with loads of components that you don't need, or doing really minor things. So they've kept it really simple, and that's really good for a control system. So I'm really looking forward to breaking this down to a schematic and having a look to see how it works, which I'll do in the next part of the video, which will be almost instantly to you, but for me it's probably going to be a couple weeks time to actually do it. So here we are about a week later, and I've done the schematic. So we can see we start very simple with the 9-volt battery. That goes to the switch. Now I've noticed this switch is a much poorer slide switch than the DB04R, which is a fairly positive rocker switch. I've found these slide switches at this price point actually degrade and rust quite easily outside, so I'm not too sure how long this would actually work in our climate in England, where it's usually quite wet for firework night and that. So that could be a failure point. Next along is the reverse polarity protection MOSFET, which is a PMOS, which I spoke about. At the top here I've put some photographs of the board so you can see which bits I'm talking about. Next across is our 3.3 volt linear regulator. I haven't worked out the capacitors because they're very difficult to measure in the circuit, and to be honest, it's going to be what the data sheet recommends anyway, so it's not going to be anything of interest. But again, you can see that's the block there that we spoke about in the last video. Then moving across, we've got the LED and the driver transistor there, which goes to the microcontroller. As I was saying, this is switched between the 3.3 volt line and the ground, and it doesn't source or sink current. Well, not much current from the microcontroller. Obviously, we're driving the transistor, so there will be some current being sunk from the transistor from the microcontroller. Right, moving on to the microcontroller itself. It's an NRF 52811. As I was saying in my previous video, that there's not many people that make these sorts of Internet of Things microcontrollers and Bluetooth devices in one, especially in this sort of package. So I think I said there was 2 companies which I could think off the top of my head, which was NXP and Nordic. This is a Nordic device. Now, interestingly, the surrounding sort of circuitry is not anything special. If you actually look at their datasheet, you will notice a very similar layout to the one that Ignite have used. This is nothing to be sort of critical of. Manufacturers of datasheets do this deliberately to allow quicker time from design to product. So I don't think there's any criticism there of them following the datasheet at all. I have designed this similar to the circuit board, so you can see it's the same layout. So the bottom of the microcontroller controls all the Q NMOSes, which we'll get to in a second, and then these over here control the battery monitor, the ADC for the voltage of the Q for the continuity testing, and then the test transistors for firing and for testing. On the back of the board, there is the production programmer for the microcontroller. So that means you could actually hack this. You could put your own program in, probably if you wanted to, if you had the micro programmer. Now, next across is the battery. Sorry about doing this very quickly, but I appreciate some people don't get bored of analyzing circuitry. So next to this, we've got the battery monitoring circuit, which is these group of passive components here. There's no active components here, so this is constantly draining your battery, which seems a little bit unusual for a battery-based product. I would expect a transistor in there so that you actually only power this when you want to take a reading and you don't power it constantly. I've done some voltage tests on this, and I found that these are the voltages in relation to the bars on the app. So, and these look quite healthy actually in terms of batteries. I think they reckon that a flat PP3 battery is about 7 volts. So they've said 7.6 volts is 0 bars, which is probably good because that still means you've still got some firing current left in it. By that point, you're not completely drained. Something I did notice was that when you decrease the voltage and then you increase the voltage again on the unit, the app doesn't change the continuity, so the battery bars. So actually, you can only go down. It can't repower. That's probably deliberate because batteries very rarely get more power in them, but especially when the unit's on. But I did find that as you go past low power, there is no sort of module shutdown or brownout. The module just starts to behave erratically and it bugs out with the software, which is a bit of an oversight, I think, for a control piece of kit. And again, there's a very logical warning about the type of battery being used because lots of brands don't offer the current sort of the amount of current you need in the space of time for this sort of example. You need a very high immediate draw that some don't have, and that's obviously to do with the internal battery resistance, etc. So now that's quickly done, let's look at the real part of the circuitry, which is the firing and the testing. So at the top, we've got this PMOS, which I was on about. I'm not quite sure what this is because I couldn't figure out from the markings what it is. It looks to me like it's some sort of either PMOS or IGBT with a gate driver because of the way it's been powered. You've got a separate power supply for logic. You've got a separate power supply for the 9 volt, which is obviously the switch-in power supply. Then you have the 3.3 volt input, which will be the firing enable. So I'm not quite sure what that package is, but it looks to me like some sort of PMOS device. Then you've got the test circuitry, which we'll worry about in a second. But then the firing strand goes right down to the individual Q terminals. And then on the other side of the Q terminal is basically an NMOS and obviously the driving from the microcontroller. So if you look at this line, obviously that means that when you fire from that top PMOS, the only resistances you've got is the parasitic resistance of the PMOS, the parasitic resistance of the RDS of this MOSFET, and then of course the resistance of the igniter. So you've got a really, really low resistance strand. So you get a very high current pulsing through there, which is what you want to fire the igniter. And this circuit is just copied across for each of the 6 Qs. Right, let's talk about testing because this is where things start to get interesting. So what they've done is they've got a switchable 9 volt supply and a 0 volt supply, and that goes through a potential divider. So it's 1K and 1K, which means you'll get half 9 volts here, so about 4.5 volts, and that is your test voltage. You've got the 1K there as well, which is going to act as your current restricting resistor, so you're not going to end up with putting a huge current through the igniter. So then on the other side of that, you have a 600K and a 100K making another voltage divider for the ADC, because obviously it's only a 3.3 volt tolerant device. I don't know what the ADC is, I haven't looked at the data sheet, but it's going to be 3.3 volt or lower. So they've reduced it again there to make sure you've got a safe reading on the ADC. So if you imagine what is going to happen, the PMOS at the top here, the firing current PMOS, is never going to be used for this side, so we can ignore that. So we've got 4.4 volts, 4.5 volts here in this junction. This junction is also connected to each side of the Q terminals. So that means that if you then put an igniter in one of these terminals, and then this MOSFET was enabled, you'd pull that 4.5 volts to ground, so you'd lower that to ground level effectively. So this is how they're going to figure this out. They're going to effectively enable this potential divider, and then they're going to pulse each of these NMOSs in sequence, and then read the voltage on that strand to see if it's been dropped at all. If it's been dropped, we know as an igniter. If it's still 4.5 volts, we know the Q is empty. And that's exactly what they're going to do. And let's look at some graphs here. So this is from the divider point there, and you can see that Q2 has an igniter in it, and you can see from this that if we count the pulses, 1, 2, 3, 4, 5, 6, so there's the 6 individual pulses, and you've got Q2 showing a much shorter pulse. It's interesting they haven't timed these pulses all the same length, which I guess is because the remote controller is doing other things, or they haven't just bothered to worry about doing that. I would have thought for a control system you'd want to make sure all your test pulses are the same length, so you end up debugging much easier, and you know it's always doing exactly the same thing every single time, which is good for this sort of system design. If we have a quick look at this graph, this again is showing you something in Q2, but I've taken this from Q8, which is here. This is the base of Q8 being pulsed, and then this is the reading from R2. So again, you can see you've got this spike, which is when there's an igniter in there, you'll get a sudden spike of voltage and it'll put it to ground. And if you actually look at that spike, zoomed in, you can see what's doing that is the capacitances. If you're ever used to seeing capacitors charge and discharge, you'll see that's a nice capacitance sort of spike, sawtooth there. Let's have a quick look at this graph, because this is quite interesting, because I wanted to see what Q9 was doing, how they're enabling the ground. So I assume the ground was only going to be enabled when they test, but that's not true. It seems the ground is almost always enabled in this circuit, and you see they pulse it between tests. I'm not quite sure why they do this, particularly if you look at these pulses, they're not short pulses. If you look, this graph down here shows you what Q9 is doing during that thing, and it's just absolute noise. I don't know why they'd make these really fast edges. I don't think this is designed. I think this is a firmware bug, and I don't know why you would keep pulsing it for no good reason, because you're not obviously enabling it or disabling it. You're just keeping it enabled and then randomly fast edge triggering it for these very, very short amounts of time, which just doesn't seem right. Now you've also got R7 there, which I can't remember where R7 is now. Where is R7? It's probably going to be on one of the Qs. No, it's not. Well, it doesn't really matter where R7 is in terms of this. I think we're probably going to be looking at it as a driver for, yeah, there we go, it's on Q2. So there it is. So we're looking at that being pulled low, because that's when R7 goes high, and you can see there what happens. So R7 goes high, so that NMOS is enabled. You get the pulse on the resistor divider effectively. So you can see it's triggering the reading at the same time that it's triggering the NMOSs below. So that's exactly what it's doing. It's enabling the divider and triggering the NMOS to see what's putting it to ground, or if anything's putting it to ground. And again, you can see from R2 there, you've got, this is on Q1 obviously, you can see you get that nice short pulse and then nothing, so that's obviously showing you there's something there. And then these Qs are obviously technically haven't got anything in, but the interesting part about this is if you count it, that's 1, 2, 3, 4, 5, 6, 7. So they've put 7 pulses in, there's only 6 Qs. So why is the microcontroller pulsing it 7 times? Again, I think this is possibly a firmware bug, in fact, because this happens randomly, but out of 5 times, probably every 2 times this causes it. So there's clearly something going on there that's not quite right. And again, if we have a look at it's another example of Q7 and Q9 interaction, where you can see we're enabling the divider and then Q9 is being pulsed erratically for some reason between every cycle. And again, as I say, that's the erratic nature of Q9. So now that's the test basically. So if it's ever been pulled low, we know there's an igniter there. Let's have a quick look at how it fires, because that's again important. So it fires for 2 seconds because we know it's designed for talons rather than E-matches. So it will fire both, but talons take a lot longer. And this is again was where Q9 comes in, because Q9 is being, and this happens every single time, it's being pulsed erratically 3 times during the firing cycle. Now if you look at where Q9 is, obviously that's this ground here, connecting this resistor to ground. So if this is high, if this PMOS is letting 9 volts in to effectively to one of these Qs which is grounded, so you've got a massive current flowing, then that's the low resistance route. So nothing's going to flow through this resistor to ground effectively, because it's got a much better route to go through an igniter. So I'm not quite sure why you would bother pulsing Q9 on that, because it just seems like you're doing something backwards there in terms of what you're trying to achieve, especially again as if you zoomed into that you'd get this noise again. So it's not even like a strong pulse, it's just an erratic noise of noise. Let's quickly jump down here to Q resistance. So I tried to figure out at what level of resistance the Q would reject a igniter versus pass an igniter, and I found this was impossible to figure out, because when you get to a certain resistance, there's obviously a bug in the firmware again, where it just becomes an endless loop of test. It doesn't stop testing. You get this really sharp pulse, and then it just locks up because you get a continual test cycle, and it doesn't stop. It just keeps going, and the app crashes out as well. If you look what's actually happening on R2, you get this sudden spike, and then you get like a midway resistance, which obviously is the higher resistance. And the app can't seem to figure out if that's high or low for some reason. Also, before that, every time you get this really, really high frequency blip, that's the 4.5 volt rail, and that's pulsing these 9 volts. So obviously could that be the firing MOSFET triggering as well? Because that would be quite serious if it was. So I don't know what that's doing there either, but that happens every single time. So clearly that has been designed like that, because it always happens. So I query whether that's good design too. I mean, this is not good design. The fact it gets to an endless loop, that should have been detected. You shouldn't, because you put a higher resistance in a queue, lock the whole system up. Right, moving on. Current draw. Just bear in mind with these traces that the settings were slightly wrong. So 1 milliamp equals 10 milliamps on these traces. I had the multiplier wrong on the scope probe. So if we have a quick look at this trace, which is effectively the current draw after the first continuity test. So interestingly, if you leave the module on without running the continuity test, it consumes about 9 milliamps average. Once you've ran a continuity test, it drops to 3 milliamps. So clearly some of the transistors are on, which maybe shouldn't be on, and that's where you've got a higher current reading. So it's interesting they haven't figured that out or stopped that from causing issues. And you can see on the graph, it might be very difficult to see this, but you can see the spikes of current, which could just be the transmission from the device, because that's going to be much higher current. But you see on average, it's about 3 milliamps with these higher spikes in it. When you test, again, you get the higher current on the square wave, which is exactly the test spike cycle, unsurprisingly, because obviously you're enabling that potential divider, which is going to draw some current. So that's roughly 3 milliamps standby. Then you run the test cycle, and the test cycle peak is about 9 milliamps, and you can see that then it goes back to 3 milliamps. So it must be that when this is turned on first time, that divider is enabled, because that's where you got the 9 milliamp draw from the very beginning. It's only when the continuity test kicks in does it realize that it shouldn't be enabled and then starts pulsing it only for the continuity checks. I could sort of understand them enabling Q9 to ground one side of the igniter just in case there's some danger. But for me, I'm not sure that it was a design feature as much as something that was forgotten about or a firmware bug. So now let's quickly look at the overview, because I don't want to make this video too long. So one thing that first comes to me as a designer is, where is R19? And that seems stupid, but there's only one missing. But if you look at the construction of the labeling of these parts, you've got Qs, and just look at the capacitors. You've got C19, C22, C23, C24, C21, C25. So why are some of these capacitors one part different, and some of them more parts, and some of them go down in range as it comes further along? You would expect all of them to be in numerical order across the Q numbers. This looks to me like there's been changes to the design as it's gone through, and nobody's bothered to change the labeling on the actual the parts, which means that this would be more difficult to bug check because it's no longer logical in terms of the numbering when you come to start probing. So these sorts of like little discrepancies are quite important when it comes to things like this, and especially like these resistors that go R6, R8, R11, R13, R15, R17. So you've got obviously some that are 2 apart, and then some that are 3 apart. And again, why is that? That seems rather weird. And again, the transistors, you would expect them all to be labeled 1 apart. So you've got Q2, Q3, Q4, Q5, Q10, Q11. So why are these 2 Qs higher? Was this originally designed to be a 4Q device and they added 2 more Qs? And that's why you've got this mislabeling. Because if that's the case, when the board was revised, they should have then changed the labels as well. So it makes sense. But they haven't. So now another issue is there's no coding of the remote to the app, which means that whoever connects first to this module gets control of it, which I think is a blatant problem when it comes to a firing module. You want to make sure that your phone is the only phone that can control it, not some random person. Another issue with this design, obviously, is that if the remote becomes unsupported at some point, the app stops working, then you can't use the module. So you've effectively just got a junk unit, whereas if you had a hardware remote like the Cobra R18R or the DB04R remote, you know it's always going to work because you've got both hardware. Now you're at the odds of Ignite staying in business and the OS manufacturers supporting apps like this, and Ignite keeping that support on your phone, and that there will be a time when obviously it becomes obsolete, and eventually that will kill off this system. The poor quality switch is obviously an issue for me. Q9 pulsing issues is obviously an issue for me. Continuity counting too many Qs randomly seems a really obvious oversight. That should not happen in a signal controlled system, and especially one that's supposedly a firing system. The fact that low power causes continuity tests to get stuck and crash out is definitely an issue for me as well. That should be managed. Battery monitoring in the app only goes down even when the voltage goes up. That's not such a big issue because I think that probably is designed deliberately like that, so you don't end up misreading a voltage as it sort of slightly flexes in use, because obviously you're going to end up, when you fire the module, the voltage of the battery is going to go down and it's going to go back up again after that pulse. So maybe they're trying to get rid of those readings. High resistance Qs ends up in endless loops. Well, yes, that should be got rid of. That's ridiculous. That if you put too much resistance in there, you end up in an endless loop on the hardware. That's a blatant firmware problem. High frequency on higher voltage spurts on the test circuit. That's what I was talking about over here, which is where you get a 9-volt burst, which can't come from the test circuit because that's only limited to 4.5 volts. So that either means that you've that is the firing MOSFET, which is pushing that 9 volts in. Either way, that clearly is an issue and that shouldn't be there. So high frequency, large current standby This is not what I'd say as a low current device. It's not necessarily labelled as one, but being as a battery device, you'd expect it to be as as minimal as possible. And milliamps, tens of milliamps these days is considered a high usage for these sorts of devices. You should be in the microamp range if you want to create a battery device. Bluetooth obviously creates the restriction of line of sight only, and this is even if you put your hands over the device, you'll lose signal. This is an issue with Bluetooth and being in the 2.4 gigahertz range. There's this sort of tongue-in-cheek sort of phrase that radio people often use, that if an object is bigger than the wavelength, then it's got a good chance of blocking it. And obviously 2.4 gigahertz is a tiny wavelength compared to something like 433 hertz like the DB04R, and that can go much longer because it's got a much longer wavelength, and small blockages won't stop it anywhere near as bad. The app does not integrate with other Ignite devices, which is quite disappointing really, because it means like the 6Q could be brilliant for doing fronts where you don't want to waste 18 Qs, and you can put 18 Qs at the back, but obviously you can't do that because you've got no integration. Quick clips again, I'm not best pleased with that. It's a lot of plastic going to waste realistically for one use. So now if we look at the actual pricing, this is where it gets interesting. So Ignite Lite is recommended retail price in the UK is 80 quid, which is £13.33 per Q. DB4 is roughly £7 per Q, and if you've got two of those, obviously it's still cheaper and you'd have 8 Qs rather than Ignite, and you'd have hard wire remote. I've noticed Happiness Firing System is now also doing the WeFire, which gives you 6 Qs, similar to Ignite, but that's only £12.50 per Q, effectively. But it is a smartphone app, so it's got the same issues, I think, as Ignite's got. So I prefer the DB04R, if I'm honest with you. The i18 recommend RRP is $224.99, and the i36 is coming at $349.99. These aren't cheap systems. And if you look at the board, then you can clearly see it says copyright Cobra firing system. So they're not trying to persuade you there that this is an Ignite separately designed thing. This is designed by Cobra, which makes all these other points disappointing to me, that there seems to be massive firmware issues in this system, which is quite disappointing, especially for 80 quid. If I'm going to spend 80 quid on something, I would have expected the designers to at least do some signal analysis. This looks to me like the firmware designer has just written the code and it seems to work, so they've got that's good enough and just sent it out rather than actually analysed the actual signals to make sure it does actually work as they expect it to. So what can I say? I like the size of the module. It's a great form factor, but there's a lot to be desired, which is a real shame.